So one application of continuity is what we call the intermediate value theorem. And this is a theorem that when you write it down, it kind of seems, and you think about it, it might seem kind of obvious, but it is very important and it leads to a lot of really nice results when we start looking at calculus more, which will be in Math Tools 2. So let's just state the theorem first of all. So let f be continuous. And this is how a lot of theorems start, especially in calculus. Continuous functions are they have a lot of nice properties that discontinuous functions might not have. So let f be continuous over a closed, bounded interval AB. Okay, so first of all, what closed means is that the endpoints are included, of course. And bounded here means that it's finite, right? So it's not going to negative infinity or infinity either on the outputs or on the inputs. If z is any real number between f of a and f of b, then there is a number c in that interval AB satisfying f of c equals z. Okay. So at first glance, it might be a little hard to parse through, but I think once you really look at what it's saying, it becomes a little more obvious. So this is saying if we have, let's draw a picture here. Okay. So if we have any continuous function, okay, so you could draw whatever continuous function you want here. So let's just draw this one here. And let's say that we have the interval a to b. Okay, these are the outputs. And then we have, so we have our outputs f of a and f of b. Okay, so we'll kind of draw dashed lines here to show where exactly these are meeting, what points we're looking at here. Then this theorem says that if you take any z between f of a and f of b, so any point between these, doesn't matter where it is, so let's say z is right here, then that means that there is a number c, so a corresponding number on the output, on the inputs, where f of c is equal to z. Okay, so we can see that this is true here. If we look at z, then we see, okay, then yeah, this is where this number c is. It's right here, right? This is where f of c is equal to z. So really this should be f of c over here, not z. Okay. So, for example, if we just take some random function f of x equals x squared, and we say, okay, let's look at the interval 2 to 4. Okay. F of 2 equals 4. F of 4 equals 16. So if we take any number in between these two, say 10, okay, then there's some number inside the interval 2 to 4 which will give us 10. So in other words, x squared equals 10 for some x in 2 to 4, right? So in particular, this is going to be some number like 3.1 or something like that, right? But there will be some number between 2 and 4. So we can hopefully see why we would need a continuous function for this, because if the function is jumping all over the place, you wouldn't be able to guarantee this. It specifically is because of the continuity, that basically what we're saying is that if a function is continuous, then it has to hit every point between f of a and f of b, right? Because it can't jump up from f of a to f of b, so it's got to hit every single point in between. Okay. So this is often used to show that a function has a zero, especially when we do that more when we look at derivatives in calculus. So a big application of this is that if you have some point above the x-axis and some point below the x-axis, and you have any continuous function between there, then you know there must be a zero, right? There must be a point where it crosses the x-axis, because it has to cross every single point between these points, right? So no matter what kind of continuous function you draw, there's no way around hitting the x-axis, right? So for example, let's show that x cubed minus x squared minus 3x plus 1 has a 0 on the interval 0, 1. Okay. And this is helpful because we often need to know that a 0 exists, and then we can maybe employ a different kind of algorithm like Newton's algorithm, which involves calculus to find that 0 for zeros that aren't so easy to find. So what this means is that we need to show, okay, let's call this f so that it makes sense when we talk about f of 0. So f of 0 is equal to 1, right? All of these will be 0. F of 1 is equal to 1 cubed minus 1 squared minus 3 times 1 plus 1. So this is 0 minus 3 plus 1. This is negative 2. Okay. This function is a polynomial, so it is continuous, right? We had the theorem we wrote down, which said that a polynomial is continuous everywhere. So by the intermediate value theorem, this does indeed have a 0 on 0, 1. Okay. If we look at it graphically, we're saying that, okay, at 0, this function is 1. At 1, this function is negative 2. It's continuous in between there, so it must cross the x-axis somewhere on that interval. Okay. And just because, why don't we just go ahead and just look at the graph just so we can verify graphically that this does indeed work out. So we'll do x cubed minus x squared minus 3x plus 1. Okay. So we can see here 0, 1, 1, negative 2, this point right here. And because this function is continuous, it must hit every point between those. So it does indeed cross the x-axis right here at 0.311.